Hi, thanks for clicking on this video. My name is Anthony. I'm a graduate student at UC San Diego, and I'm here to tell you about some work on the corners problem that's joint with Michael Jabber, Yang Liu, Shahar Lovett, and Mehtab Sawhney. We'll start by recalling communication complexity, and I'd like to motivate this by considering a real-world problem. Imagine you had two babies. For those of you who have not seen the hit animated 2010 movie Megamind, the baby on the left is Megamind, and on the right is Metro Man. In the movie, they're fierce rivals all the way back into childhood, and so I like to imagine that, as babies, they were comparing the perks that they received. How many naps, snacks, playtime, etc. And let's say there are n perks, which we can conveniently represent in binary. Now, these babies are alien species that are incredibly smart, so let's assume that they're computationally unbounded. But they're still babies, so their language is restricted to goos and gahs, or in other words, bits, and we want to determine how much they need to speak to each other to check if they received the same perks that day, or in other words, if their bit strings are equal. Now, this problem falls under the purview of communication complexity, where the goal is to understand the amount of communication required for multiple parties to evaluate some function. In the previous example, this was equality, but of course you can imagine other functions. And just to settle on some terminology, we'll say that a protocol is instructions for what to do on every input. So in particular, if I receive some input X, and I send some message and then receive some message, what should I do next? We'll measure the communication cost of a function by the length of the best protocol on the worst case input, so some sort of min-max condition. And I believe this is a natural goal. In complexity theory, we want to understand the resources required to evaluate a function, and communication is certainly a natural resource. But there's also many applications of this study. Everything from chip design to proof complexity, even more modern topics like transformers, and one particularly beautiful connection we'll see more of in a bit, to additive combinatorics. So let's return to our problem. Now, standard arguments in communication complexity will tell you that if they want to do this deterministically, they need to exchange n+1 bits. And I'll note that this is sort of the worst case, or the most bits you will ever need to communicate for any function, because it corresponds to one player sending their entire input in n bits to the other player, who now holds both inputs and can evaluate the function, and with 1 bit return the answer. So in other words, there's sort of nothing clever that they can do here. I'll briefly note that if they have some public source of randomness, then in fact they can do this with only a constant amount of communication. So we have some interesting separation here. Now, okay, you can imagine what if we have more babies, right? How does this generalize? I am not a baby, but I ran out of characters from Megamind that show up as babies, so sorry. And you can imagine multiple players now, right, holding some input and communicating as before. There are certainly some interesting questions in this model, but in a lot of ways it behaves the way you would think it would behave given sort of the two-party case. And so, at least in my opinion, a more interesting model is called the number on forehead model. Here, you instead think of each player's input as being placed on their forehead so that everyone can see their input except themselves. It's a bit strange at first, admittedly, but it's designed to sort of capture this notion of shared information, right? And this is like the extreme case of shared information. That's other than like the trivial case where someone knows everything. So if you can prove lower bounds in this model, they still apply to other sort of like visibility graphs, if you will. Now, to understand a model, it's often helpful to consider a natural function. And in the two-party case, we saw some interesting behavior with the equality function. Here, this is not so interesting because each player can just say in 1 bit whether the two inputs that they see are equal or not. And so in 3 bits, even deterministically, we can solve the problem. A more interesting function considered in the original paper introducing the NOF model is called the exactly n function. And here, each party receives some integer between 1 and n, and they want to determine whether their numbers sum up to n. Now, I won't have time to really go into it, but as with equality, there's some constant cost randomized protocol in the case of public randomness. And deterministically, there's again some trivial protocol. For example, I can tell Megamind what input is on his head in log n bits. Then he has all the inputs and can evaluate the function, check if they sum to n, and return the answer to us. So the big question here is, can you do something better than this? Or can you prove, like in equality, that this is optimal? And if this is your first time seeing it, I don't think it's obvious. It's unclear how you would prove either option. And to get to an answer, we first have to take a quick detour into the realm of additive combinatorics. Now, additive combinatorics is a bit of a broad field, so we're just going to focus on a few select objects here. The first is arithmetic progressions. A 3-term arithmetic progression is just a triple of integers all equally spaced. So something like 3, 7, 11, each having difference 4 from the previous. Now, okay, combinatorialists are interested in extremal questions, like what is the largest subset of the integers 1 through n that does not contain a 3-term arithmetic progression? And all the way back in the 40s, we had some interesting constructions, mainly by Berendt here, who showed that there is a large 3AP free set, namely one with this strange sort of quasi-polynomial density. If you haven't seen this form before, this is something that's roughly in between inverse polynomial and inverse polylogarithmic. Now, this is a very rich problem with a lot of storied history. But just in the last few years, there was a big breakthrough by Kelly and Mecca, who showed that the shape you get from Berendt's construction is in fact the optimal shape, right? And up into this sort of constant exponent on the logarithm. Now, you could ask, of course, for what happens with longer arithmetic progressions, and this is also a very well-studied question. We're going to take a slightly different direction here and consider sort of a higher dimensional problem. In particular, we're going to be interested in this shape called a corner. Now, so we're looking in the m by n grid. A corner is 3 points sort of this form, where the horizontal and vertical distances are the same. We don't care what the specific distance is, so these red triples also form a corner. And you can even think of them as being oriented the other way. So this orangey yellow triple is also a corner. More formally, it's just a triple of points, xy, x plus dy, and x, y plus d, where we insist that d be non-zero to avoid a single point counting as a corner. And again, it's a classical question to understand how large a sort of subset of the n by n grid can be without containing a corner. And the first real result in this direction was by Itai and Cesmaretti, who showed that any such A has to have subconstant density. Now, the exact quantitative behavior here was fairly poor, as it relied on Cesmaretti's regularity lemma, but at least qualitatively it showed sort of what's going on. And for a long time, the best known bound was due to Shkretov, who proved that any corner free set A has density at most inverse polylog in n. On the lower bound side of things, it turns out that you can lift sort of constructions from 3AP sets to make corner-free sets. I think for the sake of time, I'm going to go through this a bit briefly, but I would encourage you to pause the slide and look at this construction if you're interested. So in other words, you can find corner-free subsets of the grid, again, of this sort of strange quasi-polynomial density. The main result of their paper is that this shape is again correct up until the correct constant sort of in the exponent of the logarithm. So at this point, it seems like we've strayed quite a bit from our communication problem, but it turns out that there's a surprising connection here. So let's recall the problem. We have 3 players, each given an integer between 1 and n, and we want to determine whether or not there's something more clever we can do to determine if our numbers sum to n than simply one player telling another player what's on their forehead. Okay, this is the trivial protocol. Now the punchline to this comes in the form of a very beautiful connection by Chandra First and Lipton, who showed that the communication complexity of exactly n for these 3 players is essentially categorized by the fewest number of colors you need to color the n by n grid without having any monochromatic corner, which means probably what you think it means. This is just a corner where all 3 points are colored the same. Now, I'll prove the upper bound for you in just a minute, simply because I can't resist. It's very nice. The lower bound I think I'll skip for the sake of time, but I would encourage you to either try to prove it yourself or to look in their paper or some similar resource. Now, there exists coloring versions of Barron's corner-free construction. One way to do this is to just take the normal construction and take a bunch of random shifts of it. So, in fact, the communication complexity of exactly n for 3 players is not this like trivial log n, but you can get, in fact, a power savings. So we know you can do it with just square root log n bits of communication. I found this very surprising the first time I saw this. On the other hand, note that the largest corner-free subset of the n by n grid, well, this is at least the largest color class. So by our result, you can conclude that the communication complexity of exactly n for 3 players is in fact polylogarithmic in n. So all that remains is to determine the precise constant on this logarithm. And let me briefly note that our lower bound also holds for a non-deterministic variant of communication complexity, but let me not go into that. All right. So now let me try to sketch the ideas behind this upper bound. So for convenience, let's assume that n is equal to 5, just so I can sort of fit a grid on the screen. So we'll have some 5 by 5 grid of points, and they're colored such that there's no monochromatic corner. And the goal here is to use this grid and coloring to construct a protocol. The first thing we'll do is to have some pre-processing round. So each player will check whether or not the 2 numbers they see sum to at least 5. If they do, we can immediately reject, because we know when the 3rd player adds in their number, it must exceed 5. So from now on, let's assume that this doesn't happen. We'll proceed by each player looking at a particular point on the grid. Let's start with, say, Metro Man, looking at the XY point, and he'll say the color of that point. This is where sort of the log chi of n many bits comes from. And then the following 2 players will also look at a certain point on the grid, and they'll check whether or not it agrees with the color that Metro Man said. Okay. If they all agree on the color, then they'll accept, and otherwise they'll reject. So hopefully the protocol is clear, but let's see why it works. Note that they're comparing colors on these 3 points. Right? In particular, these sort of form a corner where d takes this value 5 minus x minus y minus z. I put corner in quotes here because d might be 0, but it's sort of this corner shape at least. So just rearranging, we find that we have a yes instance if and only if d is equal to 0. Okay. Now, if d is equal to 0, right, this means that all 3 players looked at the exact same point on the grid. So certainly they're all going to agree on the color, and then we accept. If d is not equal to 0, then in fact these points cannot all be the same color, right? Because otherwise we would form a monochromatic corner. In that case we can reject. Okay. So that's the upper bound sort of sketch. It's very nice. Let me now return back to our work and briefly sketch the proof of our main theorem. So we have our n by n grid of points, And let's suppose that A is a randomly chosen set of some density alpha. Okay. Now, each corner, and I put corner in sort of quotes here because we'll allow D to be 0, so these sort of trivial corners. Each corner is defined by a triple x, y, d, of which there are roughly n cubed. Now again, this is counting trivial corners. This is also counting some sort of like invalid corners that are going to hang off the edge of the grid. Let's not worry too much about that right now. This is sort of an approximation. And each corner is going to be present in A with probability roughly alpha cubed. So typically, our random set A will have about alpha cubed n cubed corners. And we know that there can be a most n squared sort of trivial corners, these corners where D is equal to 0. So as long as alpha is large enough that the expected number of corners is much larger than n squared, then there typically must be an actual corner with D not equal to 0. Okay. So this is the analysis in the randomized case. Of course, an arbitrary corner-free set is not necessarily going to look random, right? But the key point is that there always exists some large pseudo-random looking substructure. And this is what you will sort of zone in on. And the final bound that we'll get will depend on how large a substructure we can guarantee. Okay. So slightly more sort of in words altogether here, we're looking for a subset of our corner-free set A, so we'll call the subset B, of some global density beta that acts randomly in the sense that the number of quote-unquote corners in B is roughly beta cubed n cubed. And we know that this has to be at most n squared because that's the count of the maximum number of trivial corners. So I'm not going to have too much time to give you the specific details, but the point here is that B is obtained via some technical density increment argument. And we analyze this process using pseudo-random measures of spreadness coming from the work of Kelly and Mecca and grid norms coming from a follow-up with Lovett as well. And ultimately, we can find B with this density beta being like quasi-polynomial in 1 over alpha. And if you rearrange things, you get the claimed bound. Let me just conclude by mentioning that this is not a new idea, this sort of finding the pseudo-random core by a density increment process. And at least in some language or another, this idea on a high level appeared at least as far back as Roth in the 50s. And in fact, our overall sketch even more closely resembles the work of Shkredov. So really the main contribution of this paper is quantitative. Right? It's how do you carry out this sketch losing sort of minimal factors at each point so that you can conclude the correct shape. And as mentioned, several of the key ingredients are generalizations of results in Kelly and Mecca and Kelly-Lovett Mecca to a sparser regime than they're designed for. All right. I think that's all I have time to say on this, but thank you for watching, and I hope you enjoyed.